Johnny doesn't mess around. Some kids only turn to God.
So wait, is it worse for him? Is it worse for him or not? He kind of got stuck.
I mean,
What
Rick
Rick
stuff
say
is
about the Johnny
No, just like where we are, that's just impressive to be with.
No, me and Nico. We're talking about Nico.
All right, let's open up 281.
Something about 1v1 in the street.
We're going to start our next section today in Unit 5. Before break, which I know seems like a lifetime ago, we were talking about the extreme value theorem, how if we are continuous on a closed interval, we are guaranteed a very highest height and a very lowest height. Absolute max, absolute min. Can we kind of refresh our memory on where those absolute maxes and mins can happen according to the extreme value theorem? Endpoints or maxes and mins, aka those happen where the derivative is zero, aka critical point, right? Okay, at an endpoint or critical point. Perfect. So in this next section, we're going to take a look at two more theorems, not necessarily related to the extreme value theorem, but two important theorems in calculus nonetheless. Before we get started on that, though, kind of a heads up for this week. I'm anticipating a quiz on Friday, okay, for the first 3 sections of Unit 5, and you are going to have a video assignment tomorrow evening, okay, into Wednesday for class. Now that's already available online, so if you want to do some of it tonight, some of it tomorrow, all of it tonight, all of it tomorrow, completely up to you, okay, but that's already available on there. Deal? Okay, so on page 281, we're going to explore what's called the mean value theorem and Rolle's theorem for this section. So just as a little investigation here, we have a table of values for a differentiable function. If they say differentiable, they also mean continuous, okay? If you have a derivative, you know you're continuous at that spot. No hole, no jump, no asymptote. Also meaning no sharp point, no vertical point, no endpoint. Okay, so all 6 of those characteristics, we don't have any of those. So they want us to plot the points on the grid and then use those to help us answer some of these questions. So go ahead and take the time to plot those points, connect the dots, kind of see the shape of this graph. Anything exciting happen over break?
Math.
Math? Oh, that's exciting. You what? What did we blow up? Oh, yeah, I heard that too.
World War III.
Yeah, who knows what's going to happen with that.
Trying to get drafted.
Distracted with my perfect curve. I just do the best parabola I've ever done my entire life. Parabola.
I'm gonna go.
All right, upside down parabola. Looks good? Okay, so in calculus, up to this point in our class this year, we've talked about many different types of derivatives. We've had shortcuts, we've had interpretations, but one of the big meanings of derivative is a rate, how something is changing. We've used classifications like increasing, decreasing, flat, okay, aka not changing. So whenever you're looking at a derivative, you're essentially looking at the rate of change of a function, okay, how something is changing. Is it increasing or is it decreasing? But when you're talking about a rate, we can get a little bit more specific because we technically have 2 different types of rates. We have something called an average rate of change, like over a time period. What's your average changing amount? But then we can also talk about the instantaneous rate of change, like at one specific point in time, how is something changing? So I think a really good example of this, because we're all, I think of the driving age in here, is when you drive a car. So if you drive from here to the mills, for instance, you can take a look at the total distance you traveled and how long it took you to get there. And after you do that division, you would get your average rate of change. On average, how fast were you traveling? But as you are driving to the mills and you look at your speedometer, that's telling you how fast you're driving at that instant, right? The moment you look at it. So we have two different types of rate of change, something over time or something at an instant. So if we're looking at an average rate of change, if it's over time, you normally have like a beginning point and an ending point, aka 2 points. But if you're looking at an instantaneous rate of change, like how something's changing at an instant, that's indicative of 1 point. And we've kind of already briefly touched on these two different concepts, because if you want to find the rate of change between 2 points, we normally use a secant line to help us with that calculation. And if you want to find the rate of change at 1 point, that's called a tangent line, because you only touch the curve at one spot. We're familiar with those two types? Okay, so we're briefly going to identify or define them in these boxes. So average rate of change is basically the slope between 2 points on an interval. All right, this is like your secant line on a graph. You connect 2 points. Instantaneous rate of change is the slope at 1 point. What have we referred to that all year long? Derivative. Okay, and graphically this would be represented by a tangent line, where the slope of that tangent line is your derivative value. Okay, so let's go ahead and see if we can calculate or at least find some of these values beneath these boxes. So for the first one, find the average rate of change for this f of x function on the interval from 2 to 12. So average, meaning over time, okay, how fast is this function changing? So if it's an average, we're going to find the slope between 2 points. Graphically, we're going to take the point at 2 and the point at 12. And if you were to connect those, that secant line is going to represent our average rate of change. Or I guess more specifically, the slope of the secant line would be our average rate of change. So we're going to find the slope between these 2 points. Graphically, if you want to do rise over run, since we have a picture, that's fine too. You could also use the tables or the points in the table to help us find the slope. So it's basically up to you how you want to calculate it. I'm going to abbreviate this. I don't know how you want to pronounce that. AROC, average rate of change. We'll have AROC and IROC, instantaneous rate of change. Okay. Can we find the slope of this secant line? We go up 1, 2, 3, over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3 over 10. All right, what about for the instantaneous? Is the instantaneous rate of change at 4 greater than the rate of change at 6? Justify your answer. Okay, so if it's an instantaneous rate of change, we want to kind of visualize a tangent line on the graph. So if I were to draw a tangent line at 4, is the slope of that line greater than the slope of the tangent line at 6?
Yes.
Yes. All right, so we'll say we'll use derivative notation. That's better than IROC. F prime of 4 is greater than F prime of 6 because how do we know? Steeper slope. Okay, because the tangent line at x equals 4 is steeper than the one at x equals 6. All right, so these two different types of rates of change is going to lead us into these two theorems that we have in calculus, the mean value theorem and Rolle's theorem. Now, they're essentially the same theorem. There's just a slight difference between the two. That's why one is actually named after a person and the other one is more generic. Okay, so we're going to investigate that a little bit more today. So we're specifically going to first take a look at Rolle's theorem. We're going to write it down. I think we're going to get it. It's nothing too difficult to kind of grasp, but then we'll take a look at some examples of how this Rolle's theorem is applied to some graphs. So in Rolle's theorem, just like any theorem that we've seen so far this year, we have certain conditions that we have to check, and if those conditions are met, we know that the conclusion is true or verified. So for Rolle's theorem, we have some conditions. F of x is continuous on a closed interval. So I'm going to use brackets that mean closed interval. And it's differentiable on the open interval. I'm going to use parentheses for open, meaning you cannot count those. Why do you think the interval changes from closed to open? Yeah.
Because the endpoints wouldn't be differentiable.
Okay, if I kept these as brackets, we would not be able to, or be able to use the word differentiable because we would not be differentiable at A or B because those are endpoints. So continuous on a closed interval, meaning you have closed points on the end, but differentiable everywhere else in between those. Okay, no sharp points, no vertical slopes, anything like that. So we got to take those brackets away if we're going to use that word differentiable. So we're continuous on a closed, differentiable on an open. If those two things are met, okay, and we have a third piece. So we also need to check if f of A is equal to f of B. Now that's using mathematical notation, but what do you think that's telling us? F of A equals f of B. No?
I'm Megan.
What do you think, Griffin?
I'll just say like the two endpoints are at the same y value.
There we go. A and B are the endpoints, right? And if you plug in, these are x's. If you plug them into your function and the outputs equal each other, they have the same height. So we essentially have two endpoints at the same height, nothing like they're diagonal or anything like that. So the same endpoints, the connection between the two is differentiable. So there are no sharp points, no vertical slopes, no holes, no jumps, no asymptotes, nothing like that. Okay, so the endpoints are the same. If that's true, if all three of these are true, then we are guaranteed, okay, there must be a point within the interval such that the derivative equals 0. Okay, we're going to draw a little picture of this. All right, so according to Rolle's theorem, we are continuous on a closed interval. So I have a closed dot somewhere at A, somewhere at B. Those closed dots have to be at the same height. F of A equals F of B. So I'm just going to put a closed dot here and a closed dot here. We also have to connect these dots in a differentiable fashion. So no holes, no jumps, no asymptotes, no sharp points, no vertical slopes. I don't care how you connect them. Maybe something like that. Do you have a horizontal slope between A and B somewhere? Yeah, in this example I have 2. Okay, you could have 3. You could have infinitely many. What might that look like? How can you connect those 2 dots and have infinitely many horizontal slopes? Yeah? Oh, well, if you have a finite beginning and a finite end, I don't know if you could have an infinite amount in between. So a bunch of waves would be good. A straight line would also be, well, that might be finite as well because you have beginning and end. But technically, this is what's tricky though, because there's an infinite amount of numbers, but isn't there technically an infinite amount of numbers between A and B, even though you have a beginning and an end? Okay, that's called theoretical math, where you get into more theory and less application, but that's something completely different. But that would be an infinite amount, technically, of 0 slopes. So notice how if these 3 conditions are met, you are guaranteed to have a high point, a low point, or a level spot somewhere in between there. Okay, so just like any other theorem that we've looked at this year, we want to make sure that we're able to first identify, can we apply it, can we not? And then if we can, let's go ahead and try to find that special spot that the theorem says should be there. So let's see, if we look at the graph on the previous page, so you might have to do some flipping, does Rolle's theorem apply for the following intervals? So our first interval is from 2 to 14. If we look at our graph, we're definitely continuous, we're definitely differentiable. So the third criteria is, do the endpoints have the same height? 2 and 14, definitely. Okay, so that's telling us somewhere in between 2 and 14 we should have a horizontal tangent, aka derivative of 0. And that would happen based off of our graph at 8. Okay, so we'll say Rolle's theorem applies because f of x is continuous and differentiable with f of 2 equal to f of 14. Maybe we'll go even further and say that the special spot, okay, guaranteed by this Rolle theorem, we'll just give it a letter C in this case, that specific spot was 8, okay, where that maximum or minimum or level spot happened. Okay. What if we switched up the interval? What if we go from 2 to 8? It's the same graph, so we know we're continuous, we know we're differentiable. Do the endpoints at 2 and 8 match? No. So since these endpoints do not match, we're not guaranteed a derivative of 0 somewhere. And notice how that makes sense, because in this little section, there's no max, there's no min, there's no level spot. So Rolle's theorem does not apply. Okay, so we'll say Rolle's theorem does not apply because f of 2 did not equal f of 8. Are we doing okay with these 3 criteria? Continuous, differentiable, and endpoints match. Okay, we're going to take a look at one that's not given to us. Okay, no graph available. We're just going to do this based off the equation. So each of the following, determine if Rolle's theorem applies or not. If it does, then we're going to try to find that special spot where the maximum, minimum, or level spot is happening. Basically, we're trying to test to see if a critical point is located within that interval. Okay, if a derivative is 0. That's one of our criteria for a critical point. So, based off of this x to the 4th function that we have here, we're not going to use our calculator. Is a quartic graph continuous and differentiable? Quartic normally looks like W or an M, depending if it's going up or down. So there's definitely no holes, no jumps, no asymptotes, no sharp points, no vertical slopes, right? So I'd say we're continuous and differentiable. G of x is continuous and differentiable. If you're going to use a theorem, you have to first state that the conditions are true. You can't just jump to the conclusion. You have to state what you checked in order to know that your conclusion is validated. So we have to make sure that we write those conditions down. So g of x is continuous and differentiable. We now have to check the endpoints. Okay, do they have the same height? So we're going to plug in -3 and we're going to plug in 0. I think 0 is easy. We get 0. What if we plug in -3? -3 squared is 9, times 9 is 81. And then -3 to the 4th, that's 81 as well. So subtract and we get 0. Okay, so continuous differentiable endpoints match. So we officially know Rolle's theorem applies. So we know we are guaranteed to have a critical point somewhere between -3 and 0, where we have that derivative equaling 0. We're going to go ahead and try to figure out where that is. So we know it should be somewhere between -3 and 0. So let's go ahead and take the derivative. We've got 18x minus 4x to the 3rd, and we're going to set it equal to 0, just like any other critical point that we found this year. How do you want to solve for x? Factor? What do you want to take out? 2x. Okay, so 9 minus 2x squared. Alright, so this x is going to give us 0. And this one we might have to solve a little bit more. If we subtract the 9 over, divide the -2, and then square root both sides. So the square root of 9 is 3, and then the square root of 2, we don't know. Well, 1.4 something, but we'll just leave it as a square root of 2. So these are locations of where we have a horizontal tangent. But notice how we should be guaranteed at least one of them is within this interval. Can we list out of these options that we have here which ones fit this Rolle's theorem conclusion? Where's this special spot where we have a critical point within the interval? -3 over square root of 2, okay? The positive version is outside the interval, and we cannot include 0 because that's an endpoint, and we know a derivative doesn't exist at an endpoint. So there's no way a derivative can be 0 here if it's an endpoint. So we're only checking within the interval. You cannot include those endpoints. All right, so there's that special location that Rolle's theorem guarantees. So somewhere on this graph at this spot, we have a max, a min, or a level spot. What about 2? Can we check the conditions first? Before you immediately go into derivative and set it equal to 0, can we check these conditions? Are we continuous? Are we differentiable? Are the endpoints the same? Maybe we'll do continuity first, because that's usually the first one that's listed in the criteria. Is there a spot where this function would be discontinuous within that interval? Yeah.
X equals -2.
Why?
Because if you plug that in there, then you put 0 on the bottom.
Yep, and that's a no-no, right? All right, so g of x is discontinuous at x equals -2. So Rolle's theorem does not apply. Okay? This isn't telling us, I got to make sure that this is clear. This is not telling us that we do not have a spot where the slope is 0. Okay, there could be one. This is just telling us we're not guaranteed to have one. There could be. We would have to check a little bit further. This is just a guarantee or not. Okay, so it's not guaranteed that there is one, but there could be if we did a little bit more investigating. We're not going to do that though. Okay, we're just going to check to see if Rolle's theorem applies. How are we doing with Rolle's? Pretty simple. Continuous, differentiable, endpoints match. Okay, so in relation to this kind of rate of change that we were discussing at the beginning, Rolle's theorem is basically telling us that the instantaneous rate of change, okay, aka the derivative, is equal to 0, okay, a specific number. And the mean value theorem is a little bit less specific. So the mean value theorem is going to look very similar to Rolle's, but it's actually going to be missing one of the 3 criteria, which means there's only going to be 2 that we have to check. So for the mean value theorem, if f of x is continuous on a closed interval and differentiable on the open, then there must be a value within the interval such that, I'm going to do some abbreviating here, the average rate of change, okay, AROC, equals the instantaneous rate of change, aka IROC, aka derivative. So the mean value theorem is a little less specific. Notice how we got rid of the endpoint criteria. There's no statement in here that says the endpoints have to be the same. Okay, now that they can be anywhere, we have a different conclusion. So this is now telling us the derivative is actually equal to the average slope. It's no longer just 0 like it was for Rolle's theorem. So they're basically the same concept. It's just that Rolle's theorem is 0, whereas the mean value theorem is the average rate of change. So the derivative equals something for both of them. It's just a slight difference between the two. All right, so we're going to kind of explore this mean value theorem in this example. Consider the function 3 minus 5 over x. We have the graph below. Does the mean value theorem apply on the interval from -1 to 5? Is this function continuous and differentiable within that interval?
Yes.
Why?
Last continuous, there's no sharp points.
Okay, so this graph doesn't have any sharp points, so that's part of differentiable, right?
There's no flat spots.
There's no what?
I don't know. It's just differentiable.
Okay, this is definitely differentiable. Okay, so this part checks out. What about the continuity part? -1 to 5. Is there a number in here or within the interval that would not work in the function? 0, right? Because that would make the bottom 0. So we essentially have a vertical asymptote right here. I know it's not very obvious, maybe based off the picture, but since we have the equation, we know for sure that there's something going on there. All right, so h of x is discontinuous at x equals 0. Obviously, this is within the interval, so it's an issue for us. So the mean value theorem, MVT for short, does not apply. Okay, at least for that interval it doesn't apply, but maybe if we change up the interval, we could apply the theorem. So let's try that. Does the mean value theorem apply on the interval from 1 to 5? If 0 was our only issue, and now 0 is not within the interval, that means it's not an issue anymore. Okay, so we can say yes, because x equals 0 is no longer in the interval. Okay, so if the mean value theorem does apply on this interval from 1 to 5, we're going to try to draw graphically what that looks like over here. So somehow we would need to show how the average rate of change on this interval is equal to a derivative at some point. So if you were to draw a secant line through 1 to 5, so here's the point at 1, here's the point at 5. Okay, here's your secant line, average rate of change. If you were to shift that secant line up or down at all, would it eventually become a tangent line? If you kept the slope, wouldn't it eventually touch once right there? Maybe I have too many in there. Is that better? Do you see that? How if you shift the secant line, it'll eventually become a tangent line. So basically they're parallel to each other because they have the same slope, aka they're equal. The slopes are the same. So graphically we're trying to show how the secant line would equal the tangent line at some point if you did some shifting. So wherever this spot is, somewhere right there, that's the special spot guaranteed by this mean value theorem, where this average rate of change is equal to the instantaneous rate of change, aka derivative or slope of tangent line. So we're going to try to figure out what this value is. Now graphically it looks like something a little bit more than 2. So let's see if we can figure that out by hand. Okay. Apply the mean value theorem to find that special spot on the interval. So according to the mean value theorem, we got to find the derivative and set it equal to the average rate of change, meaning the slope between 2 points. How do you want to find the derivative of our function?
Online.
Oh, not online. Can we rewrite it? 3 minus 5x to the negative first. Maybe some of you thought quotient rule, which you could still definitely do. But if you bring up the x, make it a power, it might be a little quicker. All right, derivative of 3, 0. All right, derivative of the next term, 5x to the negative second. So we'll write that as 5 over x squared. So this derivative, 5 over x squared, should equal the average rate of change, the slope between 1 and 5 on our graph. All right, so since 1 and 5 are the x's, we know that those can go on the bottom of our slope formula, but then we need the related y values above those. So the y value at 5 is 2, and the y value at 1 is negative 2. So we have 5 over x squared equals 1. All right, let's solve for x. Multiply x squared over. We get plus or minus the square root of 5. Since we have two answers, maybe one or even both are found within the interval. Can we label which one's the correct one? Positive. Okay, positive square root of 5. And I don't know it off the top of my head, but the square root of 5 should be 2 point something, right? Because the square root of 4 is 2. So it seems like our little drawing or estimation there was correct. Okay, so there's our special spot guaranteed by the mean value theorem. So Rolle's and mean value theorem are really similar. Rolle's is just the derivative equals 0, but for the mean value theorem, the derivative equals that average rate of change. I'm gonna run out of time before the bell rings, but I'm gonna give you kind of an example of, well, maybe I do have time because we're drivers in here. Have we ever gone on the turnpike before where you have to pay? Okay. There was a point in time, okay, the state police don't do this anymore, but there was a point in time where they would bill you if you were driving too fast on the turnpike. Because you know how when you get those tickets, they time stamp you. So if you were at one point, you got on the turnpike at one point and then you got off at a different exit, they know the time, how long it took you to go from point A to point B. And if they do your average rate of change and that was above the listed speed limit, they would bill you because you were speeding, even if there wasn't someone on the turnpike to do a radar gun or anything, they would bill you. Now, some people, smart people, got around that by like stopping at a rest stop or something for a little bit because that would take up more time, which would affect your average rate of change. But that's an example of the mean value theorem, where the instant rate of change, how fast you're traveling at a point in time, is equal to the average rate of change. So if they knew your average, they knew you had to be driving that fast at some point, right? Isn't that tricky? Sneaky? They don't do it anymore, okay? But at one point, they had that policy. Okay, they're using calculus. All right, we'll stop there for today, but we'll take a look at the last few examples tomorrow.
Not